Let's see the layout and schematic of a two input NOR gate. At first we'll see the schematic, then the corresponding layout. So this is a two input NOR gate. This is a two input NOR gate. So this symbol of a two input NOR gate is this is OR and a NOT. This is the output. This is the input. Let's say this is A, B, and output is Z. So if I write OR plus a NOT, then we get the output as NOR. So OR is represented as A plus B plus A inverter give. This will give the output as A plus B bar, or we can represent it as A plus B bar. When we say this is a plus operator, so the NMOS will be in parallel and the PMOS will be in series. Since this is a two input gate, so we need two NMOS and two PMOS. The inputs are A and B, and there is one output, that is Z. See the truth table of a two input NOR gate. This is input A, this is input B, and the output is Z. So when input is 0, 0, output is 0, the output is 1. When this is 0, this is 1, output is 0. 1, 0, output is 0, and in 1, 1, output is 0. This is the truth table of a two input NOR gate. Now let's see the schematic diagram. Schematic diagram of a two input NOR gate. So now let's see the schematic diagram. The schematic diagram. So the PMOS is in series and the NMOS is in parallel. This is the PMOS. PMOS is in series, and the NMOS is in parallel. This is ground. This is VDD. This is the input A, input B, and this is the output Z. This is P1 P MOSFET, P2 MOSFET, and this is N1, and this is N2. Okay, now this is the source of the P1 MOSFET. This is the drain, and this terminal is the gate. The source of P1 is connected to VDD. P1 source is connected to VDD. Now this is the source of P2, and this is the drain of P2. This terminal is the gate of P2. So we know that the output is always obtained at the drain terminal. So this is again drain of N1. This is the source of N1. This is the gate of N1. This is drain of N2. This is gate of N2, and this is the source of N2. Okay, so from here you can understand that the input is applied at gate, and that is A and B. Here we have A and B. A is between P1 N1 and B is P2 N2, and the output is obtained at the drain terminal, that is P2 N1 and N2. The output is Z. Now let's see the twistor schematic. Twistor schematic of a schematic diagram of a 2-input NOR gate. How will be the twistor schematic? We know that twistor schematic means it should be like this. So before that, just draw a rough diagram of the PMOS and NMOS. This is input A, input B, and we have the corresponding. This is just a rough diagram. this is ground, this is VDD, this is input A, and this is input P. This is just a rough diagram. Now in order to draw the twisted schematic, this is P1, P2, N1 and N2. So this is P1, this is P2, this is N1, and this is N2. Now, so this is P1, this is P1, this is P2, this is N1, and this is N2. This is the source of P1. This is the drain. We had the source, drain, source, and drain. So here this is source and this is the drain. These are the gate terminals. Similarly, this is the source, drain, 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 source, and source. So drain and source. So now the source of the P1 is connected to VDD. This is connected to VDD. And the drain is connected to the source of P2. So these two are connected. And the drain of P2 is connected to the common drain of N1 and N2. Okay, before that we have to connect the gates of P1 N1 and gate of P2 N2. This is input A and this is input B. So this drain is connected over here. This is the final output. Z. These two sources are connected to ground. Okay. So this is the twisted schematic diagram of a 2-input NOR gate. Now let's see the operation of it. Let's see the explanation of the truth table. In our first condition, that is when A is equal to 0 and B is equal to 0, A is associated with P1 and 1, B is associated with P2 and N2. So when A is 1, we know, let's make the table here. Here is the input Then we have the PMOS and NMOS. This is the PMOS and this is the NMOS. When input is 0, PMOS is on and NMOS is off. When input is 1, PMOS is off and NMOS is on. Here when both are 0, then P1 and P2 will be on. So these are the PMOS. So P1 and P2, they are on, while N1 and N2, they turn off. So if you want to represent it in the schematic, then if the MOSFET is on, then it gets short circuited and this gets open circuited. So the P1 and P2, they are placed in parallel, so they are placed in series. So since they are they are short circuited, so you can see short circuited P1 and short circuited P2 and open circuited N1 and open circuited N2. This is ground, this is VDD, this is P1, P2, this is N1 and this is N2. The output here. Since the N1 and N2 are open circuited, so this won't flow, and since these two are short circuited, the obtained output will drive VDD. So here Z is VDD, or you can say this as high voltage, or you can represent it as 1. So when A is equal to 0 and B is equal to 0, the output Z is 1. Now let's see the next condition. The second condition is when A is equal to 0 and B is equal to 1. So we have P1 N1 with this and P2 N2. When A1 is 0, P1 is on. When B is 1, then N2 is on. So in this case, P1 and N2, they remain on. P2 and N1, they turn off. So this is represented by the short circuit and this is represented by the open circuit. So now when P1 and P2 are in series, so if P1 is on, represented by short circuit, P2 is off, so represented by open circuit. This is P1, this is P2. Here N2 is on and N1 is off. This is off, this is on. This is ground. This is VDD. N1, N2. Output is from here. This is the open circuit which blocks the flow from here. Since N1 and N2 are parallel, if one is open circuit and the other is short circuit, then you get the output as ground. So Z is ground, or you can say low voltage, or you can say it's 0. So when A is equal to 0, B is equal to 1, then Z is 0. Now let's see the next condition. The third condition is when A is equal to 1 and B is equal to 0, then here it's P1 and 1, it's P2 and 2. When A is 1, then N1 will turn on. When B is 0, then P2 will turn on. So here P2 and N1 will turn on, P1 and N2 will turn off. So this is represented by the short circuit, and this is represented by open circuit. When P1 is off and N1 is P1 is off and P2 is on. So off is represented by open circuit and on is represented by short circuit. This is P1, this is P2. Okay, these were in series. So P1 is open circuit and P2 is short circuit. This is P1, this is P2. N1 is on and N2 is off. So this is N1, this is N2. Because of this open circuit, this is the output side, this blocks the high voltage. This is short circuited, this is open circuit, and N1 and N2 are in parallel. So even though this is open circuit, you will obtain this value. So here Z is nothing but ground or the low voltage, or you can say 0. So when A is 1, B is equal to 0, then the obtained output Z will be 0. Now let's see the last condition. That is when A is equal to 1 and B is equal to 1. When A is equal to 1 and B is equal to 1, this is N1, P1, P2 and N2. A is 1, then N1 will be on. If B is 1, then N2 will be on. So here N1, N2 they turn on, then P1 and P2 they turn off. On means short circuited, off means open circuited. So since P1 and P2 are in series, both will be open circuited. This is ground. This is VDD. This is P1, P2. This is N1 and N2. Output is obtained from here Z. So if P1 and P2 are open circuited, then certainly there is a blocking over here. And when both N1 and N2 are short circuited, then we get the output from ground. So Z is again ground, or you can say low voltage, or you can say it's 0. So when A is equal to 1, B is equal to 1, then Z is equal to 0. So from here you can verify the truth table of NOR gate. Zero, zero, 0, 1, 1, 0 and 1, 1. So obtained output is 1, 0, 0, 0. Truth table is now verified from the schematic. Now we'll see the layout from the twistor schematic. Layout from the twistor schematic. Twistor schematic diagram. So from the obtained schematic, we can now draw the layout. The PMOS is in series and the NMOS is in parallel. We know the PMOS is constructed from N-well and P diffusion layer. So this is the N-well. And then we have the P diffusion layer. The N-well is black in color and the P diffusion layer is brown in color. Similarly, the N diffusion layer while writing the commands we write as NDiff. Before that, going for the commands, now let's see the connections. So this is okay. Let's draw the gate first. This is input A and B. This is poly. So this is the source, this is gate, drain. Again this is the drain and source, gate. This is the source, gate and drain, drain, gate and source. This will make the connections much easier. The source is connected to VDD. Okay, now this is the common drain and source. Then the drain is connected to the common drain. Okay, and the sources are connected to ground. So metal 1, the output is Z. This is VDD. This is ground. Now you have to place the contacts. This is the P diffusion contact. Or you can say this is the PDC contact. Similarly, we need a PDC contact over here. Here we need a N diffusion contact. The P diffusion contact helps in connecting the metal layer with the P diffusion layer. This is the N diffusion contact. Or you can say this is NDC. These are the N diffusion contacts that connect the N diffusion layer with the N diffusion layer with the metal layer. After placing the diffusion contacts, place the substrate contacts. So this is the N substrate contact. Or we write it as NWC, N-well contact. Similarly, this is placed in the VDD, and here in the ground, place the P substrate contact, or write it as P-well contact. So this is the layout of a two input NOR gate that is drawn from the normal from the twisted schematic diagram. Now let's see the layout from the normal schematic. Layout from the normal schematic diagram. Now in the normal schematic diagram, how will you represent? We have the PMOS in series, so we have to construct the PMOS first. Okay, this space won't be sufficient, so just erase. PMOS in series. And here. Okay, make clear. First draw the N well only. So this is first N well, and this is the second N well. So the N well is black in color. After drawing the N well, draw the P diffusion. Which is brown in color. So this is the P diffusion layer. Or the PDF layer. So now we have the N diffusion layer. Or the N diff layer. Now this is your P1, P2, N1 and N2. So after drawing the MOSFETs, connect the gate. So this is the source, gate and drain. This is the source, gate and drain. Drain, gate, source. Drain, gate and source. So this is A input. So select from here this is input A. This is input B. Now after drawing the gate, draw, this is the poly layer, poly. Next, connect the source to VDD. So we all know that VDD is drawn with the metal layer. So this is metal 1. And the sources of the NMOS, they are connected to ground. This is ground and this is VDD. Then the drain of the first PMOS is connected to the source of the second PMOS. So connect these two. The drain of the PMOS is connected with the drain of the NMOS. So this is where you obtain the output, that is Z. This is the common drain. All the connections are made with metal layer. Now in order to give the connections, the contacts, why do we need these contacts? So that the layers that are overlapped, they come in contact. Actually here the metal is not in contact with the p diffusion layer. So after placing a contact, these are connected. So here place a contact, then here wherever you want to place a contact, you have to place a contact. So these are the p diffusion contact, or you can call it as PDC contact. Similarly, this is also a p diffusion contact. This is also a p diffusion contact. After placing the p diffusion contact, that is connecting the metal layers and the p diffusion layer, connect the metal layer and the N diffusion layer. This is one. This is another contact. So this is the N diffusion contact. The N diffusion contact or the NDC contact. After placing the diffusion contacts, you have to place the substrate contacts. The substrate contacts are placed in the VDD and ground layer. So this can be one. You can place it as many as you want. So this is the N substrate contact. The N substrate contact is placed at the side of the N well. P substrate contact is placed in the other side. So this is the N substrate contact, and in commands, while typing the commands in Magic, you write it as NWC or the N well contact. Similarly over here in the ground layer, you need to place some more contacts. So this is the P substrate contact, or write it as PWC, the P well contact. So from here you obtain the output, that is Z. So this is the layout from the normal schematic. Now let's see the instantiation process. How to draw the layout using the process of cell instantiation. When we talk of the cell instantiation, in order to obtain NOR gate, we can follow two steps. The first one, very simple one, is OR plus NOT, and the second one is when it's NOR, then this is actually the fact that NOR is constructed from OR and NOT, or directly you can draw it from NOR. That is from the CMOS logic A plus B part. If you want to use OR and NOT, then you have to take the cell instantiation process. In cell instantiation process, you need, over here we need two cells, the OR cell and the NOT cell. That is the OR layout and the NOT layout. Suppose you have already drawn the layout of OR and the layout for NOT. That means the layouts of the required cells must be available. One should draw the layout of the cells before going for the cell instantiation. So cell instantiation is possible in Magic. Cell instantiation is possible in Magic. So cell instantiation is possible in Magic layout design. That means there is no theoretical significance actually. Let's go to the next page and let's see how exactly it is drawn. So let's say this is the OR cell, OR layout cell, and this is the one is the OR cell, and next we have the NOT cell. The input of the OR will be A and B. The output, let's say it's Y. The output of this will act as input to the NOT cell, and then the obtained output will be Z, which is the output of NOR. So if you take a whole thing, If you take a whole thing, then you can understand that you obtain a NOR cell by giving to input AB, and you obtain a output Z. So this is obtained, or this can be done by using a command called get cell and the cell name, and after getting you have to press X in your keyboard in order to see the inner layout. So this is how you draw the layout.